This is Kanessa Eo, and today I will cover Lecture 3 on the economics of innovation. Last week we covered the hockey stick graph. This illustrated the country's GDP per capita from the years 1000 to 2013. Two important questions arose as we covered this graph. The first being, why did the Industrial Revolution first occur, and why did incomes in different countries stagnate for so many centuries? In Lecture 3, we will address the first question, and in Lecture 4, we will address the second. The Industrial Revolution is a monumental event that changed different people's moralities, it changed social contracts, it changed intellectual disputes, and had a huge impact on the evolution of technological processes. Today, we will discuss the permanent technological revolution. It's important to note that in economics, when we discuss technology, what we're referring to is utilizing different inputs to produce an output. It does not refer to any software or hardware in particular. It's a very general use of the term. This implies that if we are discussing technological progress, we mean that we're utilizing fewer and fewer inputs to produce the same output. For example, if it takes 6 workers to produce 10 units of output in 1800, and then in 1850 it only takes 4 workers to produce the same 10 units of output, then we have experienced some technological progress over that 50-year period. For millennia, we've had very slow technological progress, and this is what we'll discuss a little more in Lecture 4. But today we'll focus on the permanent technological revolution. So this implies that at the onset of the Industrial Revolution, from that point on, we've experienced a process of utilizing fewer and fewer and requiring fewer and fewer inputs to produce the same level of output that we did at the onset of the Industrial Revolution. Now, why did the Industrial Revolution first occur in Britain in about 1800? So Joel Mokyr credits the European scientific revolution, thinking about the Enlightenment that occurred a century before. So we had this major production of scientific knowledge in that period, and the Industrial Revolution is simply the transformation of that scientific knowledge into practical use. David Landis takes a more formal institutionalist approach and describes the political systems as being the major drivers of innovation. Gregory Clark sort of highlights the informal institutions, so things like culture, the culture of saving, for example, different things like religion and so forth playing a major role in the Industrial Revolution. And Kenneth Pomeranz stressing access to a couple different resources. And so Britain's access to coal and sugar gave them a relative advantage compared to other countries in terms of being the first ones to experience the revolution. And Robert Allen is an economic historian who focuses on two simple concepts of high wages and cheap coal. And we will look at this model a little more formally later in this lecture. As we move through the semester, we're going to look at a number of different economic models, and it's important to highlight a couple of the main elements to take away each time we're covering one of these models. The first is that each of them is an abstraction from reality. Another way to think about this is, more accurately, it's simplifying reality. So we're holding a lot of things constant or omitting certain things to try and find different determinants that give us a good prediction of an outcome. The second thing that most models will generally incorporate is the idea of an equilibrium. And so we're going to focus on the different determinants and factors that sort of shift and move this equilibrium, or cause it to have some sort of gravitational pull that sort of identifies different factors and pulls them towards the equilibrium outcome. And we have a number of different ways that we can express these models. In this class, we will focus primarily on illustrating them mathematically and graphically, with graphically probably being the main source or main method that we will use to illustrate these models. And the last point is that good economic models are ones that have they are relatively clear, accurate, and useful. And so most of the things that we'll cover will be wrong in a number of instances, but in a lot of those instances, they provide a lot of utility in explaining at least one piece of some economic phenomenon. Thinking about abstraction, maps are a great tool that utilizes this concept of abstraction, similar to the way that we'll utilize it in the models that we cover. If you think about it a little more practically, when you pull up an address in Google Maps or in Apple Maps, what it's doing is it's abstracting from all of the different landmarks, all of the unnecessary turns, and basically giving you a series of events that points you in the right direction. Today we'll cover a model of innovation. This model is going to focus on 4 key ideas. And these ideas are, think of these as sort of the basic things that you need to take away and the assumptions that are underlying the model. The first being ceteris paribus, so we're going to hold all things constant other than the primary factors that we're focusing on in the model. The second being that incentives matter and firms are interested in profit maximizing. So we're sort of giving firms a goal, their goal being to profit maximize, and incentives mattering, meaning that rewards and punishments will affect the firm's actions. And the third thing here is that the relative prices will help us to compare different alternatives. So we'll see examples where absolute prices don't change, but the relative prices do, and this will affect the outcome. Now we can take a look at our model. First, we can look at the graph on the left, and we can see that the y-axis is depicting the tons of coal as an input. The x-axis is depicting the number of workers as an input. And so what this graph is going to illustrate is the combination of the two inputs, coal and workers, that will be required to produce 100 meters of cloth. You can see that this is also depicted in the table. So what we can see here is that technology A, B, C, D, and E all require a different mix of workers and coal to produce the same level of output of 100 meters of cloth. So, breaking down the different examples, A requires 1 worker and 6 tons of coal to produce 100 meters of cloth, and B requires 4 workers and 2 tons of coal to produce that same output. And so each of these different technologies has a different mix, and we can lay them all out here. And now we want to decide which technology the firm will choose. First, we'll look at the firm's choice regardless of the prices. And the first thing we'll do is use a rule to find which technologies are dominated by other technologies. We note that a technology dominates another one if it requires less of at least one input and no more of any other input. And so this will allow us to rule out a couple different technologies without even looking at the relative prices. This will sort of ease the process of elimination here. So let's look at our first example. A dominates C. We can see here that technology A requires 1 worker and 6 tons of coal, whereas technology C requires 3 workers and 7 tons of coal. Technology C requires more of both inputs, and therefore technology A will dominate C. So we can rule out C as a choice of technology for the firm. The second example illustrates that B dominates D, and we can see the same sort of example here as D requires both more of the workers and the tons of coal relative to technology B. Lastly, we can see that technology E does not dominate anything, but we cannot rule it out yet because it is also not dominated by any of the other technologies. One thing we can note about technology E is that technology E is very labor intensive, and we can see this simply by its from the table before or by its point in our Cartesian plane here. Technology E requires 10 workers and 1 ton of coal, so it's using a lot of labor power to produce this 100 meters of cloth. Now we want to know how will a firm decide between these 3 different types of technology that are left. The firm's choice is going to depend on the price of coal and labor. This "and" here illustrates that we're going to be looking at the relative price of these 2 inputs. Let's start with an example when coal is expensive. We can see in our table here that we're giving the costs of our inputs. So the wage rate of 10 pounds is the cost to each number of workers. So if you have 4 workers, it's going to cost 40 pounds. And we have our cost per ton of coal at 20 pounds. So we can see that coal is relatively expensive here, and we multiply that by the number of tons of coal required to use to get our total cost. We can see our ISO cost line here. We can see it illustrating our total cost, and the ISO cost line gives us a good visual in terms of comparing technology B to other types of technology, A and E here. So each of these technologies that are placed northeast of our ISO cost line for technology B is more costly than our technology B. Therefore, A and E can be ruled out if coal is expensive. Let's walk through a little bit of how we get to this total cost of 80 pounds. We can see that A here has a total cost of 130 and E has a total cost of 120, but let's sort of walk through the calculation as to how we get these different numbers. First, we'll start by multiplying the wage rate times the number of laborers. So for technology B, we require 4 workers, and the wage rate is 10 pounds. So we'll multiply 10 pounds times the number of workers. And then for our coal, it's multiplying the price per ton of coal times the number of tons used. And so we have 2 tons of coal multiplied by 20 pounds per ton. This gives us our equation here, multiplying it out with the wage rate and our cost per ton of coal. We have 10L plus 20R equal to 80 pounds for our total cost. Now we'll do a little bit of algebraic manipulation here, subtracting 10L from the left-hand side, and now we get the equation 20R equal to 80 minus 10L. Now we're simply going to solve for R to give us our relative price, or the price ratio of wages over our cost of coal. We can see the calculation here gives us R equal to 4 minus 1/2 L. And so this minus 1/2 here illustrates the relative price of labor. And that gives us our slope of that ISO cost line. And so we're simplifying here to the minus 1/2, but we're simply taking that wage rate of 10 pounds over the cost per ton of coal. Now let's take a look at an example when coal is cheap. So here we can see that the wage rate is still £10, but the cost of coal per ton is now only £5. And so we can see technology A here is highlighted in red. So we'll utilize this example. Using the same calculation, we'll take that wage rate of 10 times the number of workers 1. That'll give us 10. And then add that to the cost of coal per ton, the £5, multiplied by the number of tons required, 6. And so that will give us 30. 10 plus 30 will give us our result of £40 for the total cost of technology A. And you can do the same process for the other technologies and verify that A is the lowest total cost for this firm. Now, illustrating our ISO cost line given by our slope here, the slope of the ISO cost line being the relative price of labor, we can see here by our ISO cost line that technologies B and E are both northeast of our ISO cost line. Therefore, those technologies will not be within the feasible choice of the firm, and this firm with cheap coal will choose technology A to produce because it provides them with the lowest cost of production. Now, as we bring it together, we can see our two different relative prices here. So when coal is very expensive, the firm will choose technology B. That gives us the lowest total cost when coal is at the price of £20 per ton. So B minimizes our cost when coal is expensive. However, when the price of coal falls or when coal is cheap, the firm will choose technology A. And so we can see the relative prices here, or the relative total cost for technology A being the lowest when we have coal being cheap. So this illustrates it's sort of a summation of the last couple slides. And the last thing we want to identify here is that when we adopt technology A, what is our level of innovation rent? And so in order to calculate this, we simply need to do the calculation for the technology B under the cheap coal price. And so doing so, we'll have the wage rate of £10 multiplied by the number of workers 4. That would give us 40, plus the price of coal at £5 per ton multiplied by the number of tons of coal, 2. That gives us 10. So then we have 40 plus 10 equal to 50 units, or £50. And that gives us the innovation rent in this case. We simply subtract the total cost of technology A from the total cost of technology B, and we get our technology rent, or our innovation rent here, of £10. And in the long run, each of these firms will adopt technology A, because the firm utilizing technology A first will receive this innovation rent, and this will. And Joseph Schumpeter is one of the Austrian economists who sort of came up with the idea of this creative destruction that we've sort of illustrated in this model. Schumpeter emphasized the role of an entrepreneur. So this entrepreneur is the agent of change, or the innovator in this case, and they are the ones who introduce new technologies and provide different firms with different innovation rents. As a result, when one firm adopts the technology and starts acquiring some innovation rent, this leads all other firms to adopt that new technology as well in order to try and acquire some of the rent. And as a result, the old technology is now destroyed or no longer used in the society. And so this is that intuition behind the term creative destruction. The invention of the spinning mule put spinsters and spinning wheels out of work. We can see other examples illustrated through like typewriters, basically anything where you can think of that applied some level of structural unemployment in the economy would be an example of creative destruction. And so one of the primary concerns of Schumpeter was that this rise of corporations would lead to less innovation in the future. And so this is something to think about. Think about different firms or different corporations that you can sort of realize now. Think about the intuition behind things like Citizens United. If we think about corporations as people and so forth, are they stifling the innovation going on in the economy now? Returning to the spinster example, we have a couple good graphics here. The old technology was very labor intensive. It utilized a lot of workers, very few, if any, type of machinery, and this was not, we would call this capital saving in this case. Once the spinning mule was invented, we have a new technology that utilizes more machinery and fewer workers. And so now we would have a capital intensive process or a labor saving process. It's more efficient with fewer workers. And so this is one of the things that sort of destroyed different spinsters' livelihoods, because we now have machines to replace these workers. Walking through our example again with Britain and illustrating it through our model, we can see that in the 1600s, the firms were using technology B. And this is because, in this case, coal was very expensive, and so no firm would ever want to use technology A. We can see it being outside of the isocost line here. Following that, in the 1700s, we see now coal is much cheaper relative to labor. And so now firms will start to shift towards technology A, and this sort of destroys whatever the production process that was occurring at technology B, and it's now shifting all of it to technology A. Looking at how this model maps with the data, Robert Allen, the economic historian who focused on the high wages and cheap coal, we can look at first what was British labor, what was the cost of British labor relative to coal. We can see here the laborer's day wage over the price of 1 million British thermal units. We can see that Britain's price of labor was high relative to the rest of relative to these other countries and cities. And we can illustrate the same thing graphically here with the wages relative to the cost of capital in general. And we can see that wages are rising relative to capital for England in this case. And so we can see that this maps relatively well to Robert Allen's conclusions. It's important to think about whether you agree that Robert Allen's theory is totally encompassing in this case, or if he's omitting certain structural factors. Now, discussing and sort of what is the intuition behind the permanent technological revolution. We saw previously that when coal is expensive, we'll adopt technology B. Once the price of coal falls relative to labor, we'll shift to technology A. And this requires fewer inputs. So now we have much less workers involved in the production process, using more capital. And as we innovate further and further, we experience this permanent technological revolution illustrated by A prime in this case. And so Britain was the first to adopt technology A. As more and more countries, more and more firms move to adopt this technology, we can move to A prime. Different firms will find faster and faster ways with less and less inputs to produce the same output. And so now we can see how this is illustrated by A prime. Now no firm would use technology A or B. They would rather use technology A prime, being the lowest total cost. So just an illustration here, walking through the permanent technological revolution. We can see the capital intensive cloth in 1800 and an example, or a more contemporary example, of technology A prime, of what this looks like more today. Thinking about our three primary determinants of the Industrial Revolution here, The first being the cost of mining and transportation of coal fell. So this is that movement that we illustrated from 20 pounds per ton of coal to 5 pounds per ton of coal. The cost of labor increased relative to that. And so this was our second mechanism that's illustrated in the process. And then the movement to A prime gives us this technological progress continued. A couple places that we see creative destruction today. These are things where driverless cars are becoming more, or people are working on implementing this process more mainstream. Self-checkout may replace cashiers. You often hear examples of people trying to go to cashiers to sort of maintain their role in this process. And then other examples like ebooks may eventually, depending on what we're able to implement into them, may replace professors. And so these are all examples of different types of technology that will cause structural unemployment for different types of laborers. Following this, it's important to ask the question, is this creative destruction a positive thing? So we can see examples of the Luddites destroying machinery, sort of protesting this capitalist, this bourgeoisie development. We can see today cabbies protesting Uber and Lyft, these sort of ride-sharing services. And then we have some contemporary examples in the arts that sort of illustrate potential negative consequences of this development of technology. And so this is what we'll get to in in lecture 4. We'll discuss further this Malthusian trap and see how different countries were able to escape this.